interrupt me, and then we can talk about those points. All right, cool. Thanks for having me. Dominik, I'm going to talk about the Vega ecosystem, and in general, its layered abstraction for interactive visualizations. And Vega is a project that many people have worked on, and in particular, my colleagues Hem, Arvind, and Jeff. And so I wanted to make sure that they're highlighted right here on the first slide. Okay, before talking about Vega, Vega is a visualization library or a whole ecosystem of visualization libraries. Very quickly, why do we even do visualization? And I like to go back here to Herb Simon, who in the Scientific American in 1995 wrote about data and how data becomes increasingly important in our personal and professional lives. And the increasing abundance of data creates a poverty of attention. That's what he wrote or said. What information consumes is rather obvious. It consumes the attention of its recipients. Hence, a wealth of information creates a poverty of attention and the need to allocate that attention effectively. And I think visualization is a very effective way to deal with a lot of the data that we have in our daily lives and go through and focus our attention towards the important. And so one visualization that I think does that very well is this one here, which is a scatter plot. This is actually a homage to Hans Rosling, who created similar visualizations and gave talks about them. What this visualization shows is data for different countries. So we have each dot here, it represents a country. And these dots are shown in the scatter plot such that on the x-axis we have fertility, which is number of children per couple. And then on the y-axis we have life expectancy, so how old do people get. And this is a snapshot from 1995. We have the 1955, and we have the points colored by their geographic region. And so this static visualization here already gives us kind of a sense for where different countries and regions are at that time. But we can really get more insight if we're adding interactions. For instance, by hovering here, we can see the trajectory of each of these points throughout time. We can also click on them and highlight them, and then they stay there. But beyond that, we can also actually go with a slider here through time and see how all these countries are kind of moving towards the upper left of lower fertility and life expectancy, with some outliers like Rwanda, which had a terrible genocide. And so what visualization allowed us here is to get a sense of the distribution, where the points are, and interaction added another dimension to this visualization. And so I like to often also think about visualization as kind of another encoding channel that we can use. This visualization here, I created actually with Vega-Lite. So this is the library I'm mostly going to talk about today. And we're going to walk a little bit through how you would make a visualization like this in this declarative visualization language. So popping up one level from Vega-Lite. In general, there's many languages for composing visualizations, including D3, probably the most popular visualization library on the web still, ggplot, and then Vega, and also Tableau. And these are just some of the examples. There are many more tools that people have created. And they're all kind of based on one core idea that really influenced visualization design in the last decade, which is the idea of the grammar of graphics by Lee Wilkinson. What he said that most charting packages channel user requests into a rigid array of chart types. So what he means by that is that you pick a visualization type, like I want a horizontal bar chart, and then you put the data in for that chart type. But then he says, to atone for this lack of flexibility, they offer a kit of post-creation editing tools to return the image to what the user originally envisioned. If you have to pick from a limited set, there's not that many charts you can make. And so they have to kind of post hoc add more flexibilities. And so then he continues to say that they give the user an impression of having explored data rather than the experience. And so based on this idea that visualization templates are very limited, Lee Wilkinson came up with or kind of formalized this idea of the grammar of graphics and wrote this down in this book. He was not the first to like come up with this idea of like thinking of visualizations as building blocks, which is what the grammar of graphics does. But he kind of formalized it, and a lot of popular visualization tools adopted this idea from this book. The core idea of the grammar of graphics is to compose an expressive range of graphics from fundamental small building blocks, so that rather than having to enumerate every possible chart, we describe charts as this composition of a small number of building blocks, and then we can express actually a combinatorial space of possible charts using just a small number of building blocks. And so this is similar to kind of in maybe natural language, where we can compose sentences and paragraphs out of words, and we can formulate many paragraphs and sentences out of the few words we maybe know. But similar to natural language, we need rules that govern what are valid sentences, and that we usually call grammar. And so you can think of this as the grammar for visualizations. And so in the grammar of graphics, we have the following components: first, the data, which is the input data source to visualize; the transforms, like filter, aggregation, binning, etc. Data representative graphics, so what we're using to visualize the data. Encoding, which is the mapping between data and properties of the marks. And then the function that actually does that mapping is called a scale. So for instance, we go from, let's say, temperature to like a white position or a color. And then finally, to actually understand what those scales are, because those are kind of hidden functions, we have guides, which are just a kind of summary term for axes and legends that visualize the scales. And so these building blocks allow us to create tools for customized visualization design, such as D3 and Vega. They offer fine-grained control for composing interactive graphics. But these tools also require verbose specifications and technical expertise, often hundreds of lines of code for a bar chart. And so in response to these lower-level grammars for customized designs, there've also been tools developed for exploration, where we have, for instance, ggplot and Tableau that facilitate rapid exploration with concise specifications by omitting low-level details. And these low-level details are then inferred using sensible defaults to allow for customization by overriding these defaults. But these libraries often have limited support for interactions. And so our mission for Vega-Lite was to build a library that facilitates exploratory data analysis with an expressive yet concise language to specify interactive multi-view graphics. So that's a mouthful. So just going over it again. With Vega-Lite, we can create a broad range of visual encodings, including histograms, error charts, and so on. We can compose these graphics or these views into multi-view graphics, and then make them interactive using a grammar of interaction. And all of this is in one unified language. And so what I want to walk through today is the design of Vega-Lite, go a little bit behind the scenes of what how the different components work and how we built them. And then pop one level up to go about and talk about Vega-Lite in the general Vega ecosystem and why we have these different components and how they fit together. And so, as I said, I want this to be a conversation. Please interrupt me, and Kai, maybe you can monitor the chat a little bit if there's somebody asking something. And I don't notice this in the little Zoom chat window here. Any questions before I go into the design of Vega-Lite? Okay, you've probably heard this before. It's like a general intro, but I want to make sure we're all on the same page here. So in Vega-Lite, let's start with the single view specifications. And let's talk about how we actually make visualizations. We usually start with some kind of data and want to convert that into a visual representation. So for instance, we have maybe weather data about Seattle, like the temperature, precipitation, the weather type, and so on. I want to have a strip plot for the temperature. So in Vega-Lite, a single view is specified by encoding the data properties as properties of marks. So that means the different fields are encoded as properties of a visual mark. The mark in this case is a tick. So the strip plot is a tick with the x field, with the x encoded as like some field. So here the temperature, for instance, as the x position. This is a quantitative variable, meaning it's kind of continuous and numeric, and we can talk about its magnitude. So in Vega-Lite, that's specified like this, where we have start with the data. So say the mark is a tick, and then the encoding is saying the temperature should be on the x field here. And all of this is in this portable JSON specification. What happens behind the scenes is that Vega-Lite infers sensible defaults for things we haven't specified. For instance, we talked about the different components, right? Data, marks, encodings, scales, and axes, and guides. The scale here is automatically inferred to be a linear scale because we have a quantitative variable. And the domain is inferred from the range of the data with some like nicing. So in this case, minus 10 to 40. And then we have the axis, which has a title automatically inferred from the field. And we also added grid lines to make it easier to track the individual items. And so that's happening behind the scenes. That's, I guess, a fairly straightforward default, but we're going to go into some more complicated ones as well. And users can override all of these defaults to customize the chart. So one thing in a strip plot, while it's great to see kind of the spread of temperatures being from like minus a couple of degrees to 30 somethings, we can't really see how many days there are in each of these ticks. And so what is the visualization that would help us see the count in each of these bins? How would we see the distribution better? What's the visualization type that allows us to do that?
So what would you say, histogram?
Yep, a histogram. So let's make a histogram. What's a histogram? In terms of like the grammar of graphics. What kind of mark and what's the encoding?
So would you say the mark is the line, so the encoding will be the y position?
So it's not a line, it's a different mark.
Mm.
Right, we have a rectangle.
Yeah.
R. Yep. And then we actually have not just one encoding, we have two encodings. So we have y. Yep. Y is the count. What is x? What is x in this case?
So yeah, someone says the x will be the range or the bins.
Yeah,
and y will be count.
Yeah, so y is the count and x is the binned temperature. So the binned field. Okay, so that's really all we need to know to then make the chart. So to make this bar, we use instead of the tick, we switch to we can go actually step by step. So first, let's do the binning. So we bin the variable, and now we have them have the ticks kind of on top of each other. We then use y for the count, and you see that the tick automatically rotated, and that's because the default orientation of one of those ticks is along the quantitative dimension, or along the continuous dimension, and the binned dimension or binned field is kind of becoming somewhat continuous, discrete, and so Vega-Lite automatically flips the orientation of these tick marks, and then we can just change the bar, and boom, we have our histogram. And behind the scenes, there's a couple calculations going on that we don't actually have to specify manually. So if we were, for instance, to look at the kind of the SQL query that gets generated here, we have the bin temperature and the count selected from this kind of bin query here over the weather data. And the cool thing is you don't have to worry about this query being generated. That happens kind of all behind the scenes. All right, there's a couple more sensible defaults that we have here, in particular for this binning. And I think that's pretty interesting because there's many components interacting with each other. So we have these sensible defaults for binning. Right, we have, in this case, from -5 to 40, but that's kind of a choice that depends on different factors. And it actually depends on the guide and also bin parameters. So if we have, in this case, a position encoding, right, X is a position encoding, we have a quantitative axis with many bins. So you can kind of see the continuous range. And we have many bins as in, I think I have to count this, but more than you would have maybe in a different encoding. In particular, more than you would have in color, opacity, or shape, where the guide that's created is not an axis, but a legend with range labels. And we would have fewer bins when we use color, opacity, or shape. And that's intentional because our perception is much more accurate when it comes to position encoding than it is for color. And so Vega-Lite makes this choice to use fewer bins for temperature and for color encodings. And so here what you see is multiple kind of pieces of the grammar interacting with each other. Questions about this? Oh, I see the chat actually. Oops. Good. All right. Okay. So having a grammar, you still see the screen, right? Do I have the right screen shared now?
Yeah.
It's all good? Okay, cool.
Yeah, and also there's a question in the chat that says, and how easy is it to change away from the defaults? So for example, people want to change the bin size or number of bins, I assume.
Good question. So I showed it earlier for the scales and axes, how to kind of how it's written, and you would override it exactly in the same way. To override the number of bins, so if you go back to the previous example here, to override the number here, you can really only override the number of bins. You cannot say, oh, I want position to now use a legend, right? That it always has to be an axis. But you can change the number of bins very easily by, instead of saying bin true, you say bin max bins and then a number, and then that will be used as a guide for the binning algorithm to determine the bins. So that's how you override it. Okay. Yeah, you're welcome, James. All right, so now that we made a histogram, we can see kind of distribution of the temperature, but if you also want to break it down by the weather type, like it's like maybe the high temperatures, are they correlated with sunny weather, and the lower temperatures more with rain and snow? We can add an additional encoding using the color. And now we get a histogram that shows us the dominant weather type on days with a particular temperature. And again, there's the defaults that are automatically created, in this case for the colors, but we can override them to create colors that are maybe more resonant with how we think of these different types of weather. And so that's again how we override the defaults. And what we have here is now a histogram with color, which creates the stacked histogram. And there's again a lot of sensible defaults that go into this. Here, what actually happens is that we automatically stack the bars on top of each other in each bin. And that's very important because otherwise the overall shape of the histogram would not be preserved. Right here you see if we're stacking, we're preserving them, and otherwise we don't. Again, this is also a thing you can override. And what's interesting about this default is that it is an interaction of the channel, which is the color, the mark, which is the bar. And these together enable automatic stacking, which is kind of a layout transform. And well, if you didn't do this, we would have this chart on the left, which kind of looks like a reasonable chart. But actually, this is a lot of bars stacked on top of each other, and you can't even see some of them anymore. And so that's very problematic, right? Like snow is completely gone there. So if I were to draw the lines, you can see this overlap. And so to prevent this overlap, Vega-Lite automatically says, well, we should stack these bars to avoid this. And there was one more question from James about, is this a special case of bins having different widths? 0, 10, 10, 15, 15, 16. In this case, the bins are always kind of size 5, but you can override them to be like a different size if you wanted that. Or you can also actually set the bins manually if you wanted exactly 0, 10, 10, 15, 15, 16, and so on. You would have to set that manually. Can this be different sizes within the same plot? Yes. Yeah, you can set the bin thresholds, is what it's called. And then they can be all different sizes. That's possible. This bins property, so it can be either a Boolean, true or false. False doesn't do anything, but it can be true, or it can be an object that can specify the max bins, the threshold, the start, the step, or various combinations. And you can check in the documentation about these. Okay, so going back to the sensible defaults here. All right, we got the stacked histogram. And well, while this is already a good chart, it still makes it kind of hard to compare some of these bars because they don't share a common baseline. And so we can again convert this chart a little bit by making a small modification and switching from color to column. And that all of a sudden creates a trellis histogram. And I think this is where this power of the ground of graphics comes in, where you make atomic modifications and you get a very different chart that lets you explore and analyze different aspects of the data. And so this is the first example of a layered or multi-view composition chart. And Vega-Lite has different composition operators. The first one I already showed you, which is faceting. We also have layering to put different marks on top of each other. Concatenation to put completely different independent views next to each other. And repeating, which is a concise data-driven way to concatenate many charts. It's a kind of a convenience for a specific concat. So if we're going back to this weather data here, and now we have a chart that shows the precipitation. So just the amount of rain for different months of the year. We have on the x-axis the month, but in this case it's kind of binned, but bin for time, which we call time unit. And here it's binned by the month, so that each month gets its own bin. And then on the y-axis we show the aggregation, the mean of the precipitation. And so this chart shows us kind of the overall distribution, but we can layer it to add another chart. Here in this case, one that shows the average of the precipitation as an overlay rule line. We can also take this chart and concatenate it with another one, for instance, taking the same chart and making a similar one where we show, instead of the average precipitation, we show the average temperature. And really what you see is that the only difference is the field. And so there's a shorthand for this, which is the repeat, where we can start with exactly the same specification. We then say, let's do a repeat over the row, where we use the following properties or fields: precipitation, temperature, and then wind. Right, that's up here, this repeat. And then we replace in the y the reference to the specific field with the repeat, so that now each chart gets its own field on y. And so as I said, this is kind of a shorthand for concatenation, making it very convenient to create these 3 charts in just a specification that fits on the slide. We can even use this repeat to go into 2 axes, into column and row. And now we get this scatter plot matrix or SPLOM, where we can compare all the different fields against each other. And so now we use layering, concatenation, repeating, faceting in different charts. And one thing we can actually do is create this whole dashboard, which is a composition of all of these charts. So we have at the bottom there a couple individual views that are faceted, repeated, or layered. We can then take the layered one and repeat it as well. So we can hierarchically go through this and then concatenate these charts and deconcatenate these and have this whole view specified in just a single specification. So you can create whole dashboards in just one specification, and the data can be reused and optimized across these different charts. And this gets particularly interesting when we're not just making these charts static, but interactive. And so we're going to look at that next. Yep. I think I said that was cool. All right, let's talk about making charts interactive. But before I go there, any questions about view composition? I don't know how faceting really works. Faceting is one of the hardest things I feel in charting. There's so many subtleties to exactly how to get the data transforms set up. Excellent. Jim says this is a really useful explanation. Thanks. All right, let's make these charts interactive. And this is, if you've seen a similar Vega-Lite talk before, this is slightly different because we updated the way interactivity works from the original Vega-Lite paper. And this was introduced in I think Vega-Lite 5, which is different way to specify, slightly different way to specify interactivity using something called parameters. And so this dashboard that we just looked at, is really powerful for looking at multidimensional data. But if we want to further interrogate data, we really want interactivity so that we have these linked views to uncover hidden relationships. And this was the motivation that we started out with when I showed you this chart from the different countries and their life expectancy and fertility. Interactivity really added another dimension. And so let's look at how Vega-Lite allows us to make charts like that. And it does that through these variable parameters. And in the simplest form, a variable parameter is just like a variable in other programming languages that you might be used to. So going back to this example here of layering, where we had the precipitation and then a rule mark that shows the average precipitation over this line. So here we draw the average as, the rule as the average of the precipitation. But what we can also do is instead of letting it compute from the data, we can also hard code the value and say the rule should just show the value 3. Maybe it's some kind of threshold of a precipitation level that we want to show here. We can then take this parameter, this number 3 here that's in the spec, and actually pull it out into a param. And so instead of having this magic number here in the specification, we can give it a name and a value, and then refer to it using an expression. And so now you can use this constant maybe in multiple places in the same chart. Not much happened so far, but the cool thing is this param, we can also bind it to an input. So what does that mean? We can have, for instance, the slider and bind the threshold to this this input slider. And now if I move the slider around, the threshold value changes, and that changes the Y position of the rule in the specification. Yeah, questions about this parameter? I guess it's kind of expected, similar to like programming in other languages. Okay, we I'm just going to replace here the code for the first chart with the actual specification, which was a bar mark, right, with an X and Y encoding. And what we can also do is use this threshold to encode additional properties of these bars. For instance, we can say, let's make a bar change its opacity if it's above or below the threshold. And we have the threshold value, so we can just say if the precipitation is above the threshold, set the opacity to 1, otherwise to 0.5. And so now, if I change the threshold, you see that the bars change their opacity. So there's a couple of questions here. Can you do things like change the bar colors if they are above the threshold? Excellent question. That's exactly what we did. We changed opacity, but we could also use change color, for instance. I mean, opacity is kind of like color here in this case. And the talk is, so James, like, what am I going to talk about next? And the talk is recorded. I can post the slides, but it's also all in the documentation. But I can post the slides. So. Or maybe email me, actually, that's the easiest. Then you don't have to like find it. All right. Cool. All right, James, next, let's talk about selection parameters. So this is now taking this idea of parameters and adding this concept of selections, which we introduced in the Vega-Lite paper, to really make interactions go beyond just simple sliders. And so now we can actually directly interact with the underlying data in the chart. So looking back at just a simple specification here that shows, in this case, data about cars. We use a circle encoding to show the horsepower on X and the miles per gallon driven on the Y-axis. And we'll be coloring the points by the country, the origin. And so this gives us kind of a sense of the distribution here, where we can see higher horsepower leads to lower miles per gallon, and where certain countries are. So now we can add parameters that say are certain points that like include or exclude certain points from this data set. So here we create a selection which selects points, and we're calling it selected. So this is an arbitrary name that we're just going to reuse in different parts of the specification. We can then use this selection to conditionally drive a color encoding. Here saying that if a point is selected, we're going to use the origin to encode the field to show this as the color, and otherwise we're just going to make the point gray. And so now you can interact with these points, click on them to have them be colored by the origin, and otherwise just gray. Besides just selecting a single point, you can also select multiple points using the shift key. And again, this is kind of very similar to what we've talked about when we talked about visual encodings. There's a lot of defaults that are happening under the hood here for what does it mean to, for instance, include and exclude a point. What's the interaction? In this case, it's the click, right? You click on a point, then it's selected, and shift click to add to the selection or remove from the selection. We can change the underlying defaults of how one of these selection parameters works by, for instance, overriding the trigger and say, well, instead of on click, we'll do it on hover. And so now what you get is you get the points selected when you hover over them. And if you shift, then it just keeps adding to the points. And so you get this kind of brush or paintbrush-like behavior. So these are point selections. The other kind of selection parameter Vega-Lite has is an interval selection. So rather than selecting individual data records, we're now kind of selecting in the domain and selecting ranges. So here we just switched the type from point to interval. We can just leave the condition and everything the same, but now you can draw a brush. So Vega-Lite automatically instantiates the code to create a brush. And so now points are selected if they are inside the brush. All right, so these are the two selection types, intervals and points. And there's a question. I don't quite understand how this all works together with the massive overplotting in this particular data set. I'm not sure I fully get the question. Yeah, there's lots of points on top of each other. But basically what happens is that the brush creates kind of a filtering condition that says we only want the points that are within a certain X range and a certain Y range. And those are the points that are then in the selection, which then get rendered, or all of the points get rendered, but the points that are in the selection will get colored by the origin and the rest will be colored gray. So that's what happens here. So if you draw, I can show this the animation again. For drawing the brush, you see the points that are in the brush get colored, but the ones that are outside don't. But you can see the points are also slightly, some of the circles are maybe slightly outside the brush. And it's because we're only taking the center for the filtering condition. It's not a brush. We only hide, so we're only if it's a brush, we're highlighting all the points that are in that rectangle. If we're doing the individual point selection, we're only selecting one point. If we're clicking, just like the one that's on the top. Yeah, if there's multiple, it would only be one that's selected. If you want to select all the points of one origin, for instance, you can do that. And that's using something called selection projection. And so let's look at that actually here in action. One way we can restrict a selection is by, for instance, instead of saying it should be on X and on Y, we can say we only want one D interval. So here we're saying the encoding of the selection should be restricted to X. And so now you get a brush that can only be moved along the X-axis, but not the Y-axis. And so the filtering condition becomes a simpler one. You can also restrict to, for instance, instead of X, you could use color. And now if you clicked on a point, and then you wouldn't use interval, you would use point. And then if you clicked from one point that is in Europe, all the points from Europe would be highlighted. So that's also an option where you can restrict the specify the selection. Another question is, how can you select one point if they are plotted on top of each other? It will depend on the order in which they plotted. They have too much overplotting. Yes, it's absolutely a problem in this chart. There's overplotting going on, and you can only select the point that happens to be rendered on top. There is a way to change the order, but yeah, you would only be able to select one point. So it's probably not the most useful thing in this case. So usually I would say point selections make the most sense in like bar charts, where you have the marks not plotted on top of each other. Another question is, are you able to have two AND conditions or two OR conditions? Yes, you can AND and OR the selections. I don't have an example here, but it's in the docs. You can also use different plotting characters and ideally not solid plotting character. Yep, instead of using a circle, you could use just the outline of a circle. Or yeah, make the chart a little bit bigger so that the points are not as much on top of each other. Yeah, overplotting and dealing with overplotting and lots of data. That's another talk that I can give. So you have to invite me back and then I can talk about big data and dealing with that if you want to. But in the interest of time, I'll walk through one more thing you can do with selections, which is also binding them. So previously, we bound a parameter to an input so that you can use the slider to change the threshold, right? We can also bind selection parameters to inputs or to also scales. So what does that mean? We're doing something very similar to what we did before, right? Where we created a two-way binding between the input or binding between the input and the value of the parameter. Now we're using the scales and bind them to the interval. So what happens here? You could try to guess, maybe, and you try to think like what happens now, but I'm just going to show you. What happens is that we can now now scroll and zoom the chart. Because what happens is that, it might feel a little magical here, but what happened was that we created a two-way binding between the selection and the selection parameters and the scales, in particular the scale domain. So the selection is populated with the scale domains, right, which was the whole range. And then when you change the selection, we drive the scale domains. So kind of what happens under the hood is that we have the scale domain set based on this on the selected parameter. And so that's how you can do zooming and panning. All right, and this selection parameters together with view composition is where really a lot of power can come in. So we can, for instance, make make these two charts here that show stock prices over time. It's just the same chart twice. One is just a little shorter, and so these two arrow charts. And we can add a selection to the first chart to select a particular interval. It's just there. It's not bound to anything yet, so nothing happens really. But we can then use this in the second chart to set the domain of the scale. So here we're not letting Vega-Lite do this automatic binding to the scales in this first chart, but we're using it to drive the scale domain in the second chart. And now we get this focus and context interaction where you can see the details of the selected range in the bottom chart. Right, it's the same concepts, just apply now to the concatenated chart. Or we can use it to build out a cross-filtering interaction. So here I'm going to use an example of flights. So we have one histogram that shows the number of flights in particular hours of the day. You can see most of them are between like 6 a.m. and then 10 p.m. And we're just binned and counted. So pretty standard chart. We can use repeat to create 3 of those charts, one for the hour, one for the delay, one for the distance flown, with the repeat operator. And now add a layer just to show the which data we might be focusing on using this gold. So just 2 layered of the same data on top of each other. So just blue and gold on top. And now we can add a selection parameter to the blue chart to just have an interval selection projected onto X. So it's just, you can just brush along X. And then use it to drive, right? So now we can just brush, nothing happens yet. But we can use the selection parameter to filter the data for the second chart. So this happens before the binning and aggregation. Now the data gets filtered. And so now when you select, you can see we have those bars that show exactly the selected range in the other charts. And all of this, I don't have a full code here, is about like 36 lines of JSON. And so I think here really comes this power of composition in, where we can make a pretty complicated chart using just these small number of building blocks. And so with Vega-Lite, we have really an expressive language to create various charts, including like these maps of London and histograms and so on. And because Vega-Lite allows to create this expressive range of graphics, it's been adopted in various places, including as actually the default plotting library in JupyterLab, a popular data science platform for data science. We have about 1 million downloads on NPM, which is a hosting site for JavaScript projects, and about 2 million per month on a CDN. So this, I guess, people looking at charts with Vega-Lite. These are just proxies. It's also used for teaching or for research at various universities, also for teaching, including also at CMU, where I built on these principles of like small building blocks to teach students about visual design, and used like in many other places. And Brian Granger, I think, summarized why it's kind of become so popular, because he says that Vega-Lite is perhaps the best existing candidate for principled lingua franca of data visualization. because it follows the ideas of the grammar of graphics very closely and allows for fairly custom designs using just a small number of building blocks. Lee Wilkinson actually posted on our GitHub once or a couple of times about different visual designs, and was generally a fan of Vega-Lite, which was really exciting for us. Yeah, unfortunately passed away recently. But yeah, the discussions on GitHub are still there, and great. He was very excited about Vega-Lite and called it as one of the closest implementations of the grammar of graphics. Okay, so that's the design of Vega-Lite. Any more questions? Great questions so far. Thanks for all of them. The next version of ggplot, ggvis, was based on Vega, but development feels like it has stalled. Do you have any sense of where it's going? Yeah, it's kind of stopped. I haven't seen anything happening there, but I think you would have to ask Headley about that. Yeah, lots of reasons why not. It makes sense.
I have a question, if that's okay, Dominic.
Yeah, go for it.
Hi. That is really like magic. As someone who's actually tried to do similar things with D3, it certainly doesn't take 36 lines of code. So I have a question about the default choices on things like the binning parameters based on the channel that you're using. Is that based on empirical research, or is that a rule of thumb that you've come up with? I guess in some cases it will be, in some cases it will be pragmatic.
Yeah. So the thing you said about D3, one thing that's actually very important also to think about is that Vega-Lite and Vega use D3 quite extensively. So we're definitely building on the shoulders of giants here.
Sure. Yeah.
D3 really has it allows for a lot of flexibility, and we use like the scales and a lot of other
yeah, absolutely.
library. Yeah, so a lot of the design of Vega-Lite is based on what we've seen in other libraries in, like, for instance, D3, in Tableau, in ggplot, and so on, which is itself based on either years of design or research. These particular binning parameters are kind of a mix, right? We know from work going back to Cleveland McGill that position encodings are more have a higher resolution than color encodings, and so research has shown that we should probably have more bins for position than for color. But the exact parameters, that's something we kind of eyeball a little bit, right? That's like where the design aspect comes in. There's thousands of design decisions we had to make, and it would be impossible to find a paper for each of them. But that's why it's kind of a design challenge.
Sure, and I guess you can always override the defaults if you have a strong reason for wanting it a different way.
Yeah, the other challenge is that a lot of questions depend on your specific data and use case, which is something we don't even know. So sometimes a default is also just like a reasonable value to start with, so that you hopefully don't miss an important insight. Yeah, especially binning. There's actually a paper from Vijay just that I saw she posted recently about binning algorithms that look at Tableau public and kind of determine good bins from there. It goes beyond just making a reasonable default. Okay, there's one more question. In your declarative language, there are functions like aggregate, but I suppose that one is not able to define new functions. So aggregations, you can there's a number of aggregates. You can also define custom expression functions that you can use in your your transforms. Most expressions are just limited to being expressions, just in a subset of the JavaScript language. There is a way to add custom expression functions to the Vega-Lite runtime, or sorry, to the Vega runtime, and then refer to them. So that's possible. All right. Can answer some more of those questions at the end. I'm just going to quickly go over the. Let's pop up the level here and go talk about Vega-Lite in the Vega ecosystem. And really, the axes we can think about here are the ease of use and expressiveness axes, which are often going in opposite directions. The easier something is to use, often it becomes less expressive. Like kind of anything in the world, there's trade-offs to be made, and so we have to make trade-offs in these libraries as well. And so at the lowest level, highest expressiveness, we have these basic libraries like SVG, Canvas, like graphics libraries. Then on top of this, we have Vega, which actually consists of multiple kind of sub-components. We have Vega, the Vega language, which renders or compiles to a Vega data flow, which is a declarative data flow. And then that renders a scene graph that then gets rendered into the SVG and Canvas. Now, on top of this, we have higher-level Vega-Lite. So we talked about Vega-Lite enough. So what is Vega? Vega is a visualization grammar, and it actually came before Vega-Lite, and this is what Vega-Lite compiles to. Vega was the first comprehensive approach for declarative specification of interaction techniques, and it's heavily inspired by D3. And when we have a Vega-Lite specification like this one here that shows stock prices over time, so we have on the x-axis date, y the price, and then the color is the stock symbol. We can compile this Vega-Lite to Vega. So lots and lots of compilers. So Vega-Lite compiles to Vega, and well, it's a fairly long specification where we can focus here on a particular aspect of it, and actually see kind of a mapping of how the Vega-Lite compiler determines different aspects. So the data gets put, for instance, into like the source up there, and then the source gets referenced in the facets. The mark appears as the mark also in Vega. But it affects a couple more things like the grouping, and so all of these aspects are determined by the mark type. We have then the X encoding, which both sets the scales and axes, right? Those are instantiated, as well as the fields and the encoding in the mark, in the line mark. The Y encoding also similarly affects different parts of the Vega specification, and the color. And so kind of everything is accounted for somewhere, but there's many different aspects of a Vega specification that can be affected by one property in Vega-Lite. So then this Vega specification gets compiled down to the Vega data flow, which is a reactive data flow graph with efficient incremental processing. So you can update the data, you can update a signal, or update a param, and then only recomputes the parts that actually have changed. Yeah, and so this Vega data flow then generates a scene graph, which is then rendered using Canvas or SVG. And so that creates this whole stack of libraries. And what's cool about them is that kind of at any point you can go in and change things. So you could start, for instance, making a chart with Vega-Lite, render it to or compile it to Vega, and then modify the resulting Vega. If there's something you cannot do in Vega-Lite, but you can do in Vega, right? Because we have more expressiveness at that level, you can go in and change things there. I think that's a really powerful thing about the Vega ecosystem stack, is that each of the layers are designed and are something that people are supposed to read and modify, rather than just being kind of an intermediate representation that you should never look at. That's kind of in the box. You could even go and modify the resulting SVG if you really wanted to customize that. And I've certainly done that when I've created figures for papers. Generated the SVG and then modified it in Figma, for instance. Yeah, so we have this whole stack of libraries. And we can even go not just below, but also above and build libraries on top or UIs on top of the visualization languages. We have a number of things, including libraries that extend the functionalities of Vega-Lite or provide like additional helpers. Like we have themes, we have tooltip support, embedding visualizations in Vega and Vega-Lite on websites using Vega Embed. And then UI tools like Voyager and Lyra for custom designs and data exploration. Those are separate talks in themselves, so I'm not going to go into those details. And then we can also have different libraries that generate Vega-Lite. So again, adding maybe another level of abstraction on top of Vega-Lite. Right, Vega-Lite is already fairly concise, but you still have to specify the encodings and the marks and so on. And maybe writing JSON is not the most natural thing to do. So there's APIs in programming languages for authoring visualizations, like Altair in Python, Vega-Lite API in JavaScript, Elm Vega in Elm, and many other ones, which provide native APIs in programming languages. And they generate the Vega-Lite JSON, which is then passed to the Vega-Lite via JavaScript library and then rendered. And so here's an example in Python where somebody imports Altair and then creates a chart. And it just feels more natural to Python developers to do it that way. But you still have to specify all the things like the marks and the encodings and so on. And so we've extended Vega-Lite again with in a language called or a system called Draco, where we encoded Vega-Lite with additional design best practices. So this is again based on research and some like careful design, where we said, well, can we automatically infer what a reasonable mark type is based on the encodings that you want? Or if you don't tell us anything, can we automatically determine reasonable encodings? Or if you tell us, oh, I want this field, maybe we should add the binning and the counting for the histogram right on the tick plot in the beginning. Maybe we should add that automatically. So all these defaults we've encoded in the system called Draco, which is a declarative knowledge base of visualization design best practices that the constraint solver then automatically can apply to create reasonable designs. And we're actually working on Draco 2, which is, so Draco 1 was published as a paper at InfoVis in 2018. And we're working on Draco 2, which is a more extensible version and also actually documented version of Draco, where which you can use now. It's actually pretty much done, so you can use it. So this whole stack of abstractions, really, like Draco wouldn't have been possible without having all the libraries below. And so some lessons that we've learned from building this is that really that having this layer of abstraction is really useful because you can have extensions at any layer. Declarative design, which I didn't talk much about, versus imperative design. But I think it enables a number of really cool things like automatic chart design, automatically inferring these best practices, inferring from intent what we should do, like automatically optimize the code to have a more efficient execution, or have accessible charts where somebody who uses a screen reader can still access the data. So in Vega-Lite, if you make a chart, we actually automatically summarize the axes in summaries for screen readers, so that you don't have to hear all the different labels, but it actually summarizes this a linear scale, a log scale, what are the ranges, and we also provide accessibility information for the individual marks. And that's something we can do because it's declarative, where we have this flexibility to just add that to an existing specification. And it also makes it easier to generate code from GUIs. By the way, accessibility is a whole other very interesting topic that recently there's been a lot more happening in the Viz community. Lots of exciting things happening there. And yeah, in composition, a small number of building blocks really allows for an exponential design space. And so I'm a huge fan of this composition approach. And that's the Vega ecosystem. So today I talked about the design of Vega-Lite, and some of the design decisions and best practices went into single view specifications, layering, and interactivity. And then we looked at Vega-Lite in the context of the larger Vega ecosystem and what this stack of layered abstractions enables. And so thanks so much for coming, everyone. Here is my contact information if you want to follow up on anything or learn more about my research. I'm also on Mastodon now, so you can come there. And also my group at Carnegie Mellon University, the Data Interaction Group, has a website where we feature our research and talk about different projects we're working on. And with that, I'll open it up for more questions.
Thank
A little
you.
bit over time. So thank you.
No, that's fine. I mean, and thanks. This is an excellent talk, and also, yeah, we run slightly over time because we're having questions in between the talks and during the talk. That's okay. I don't see.
If you want to stop the recording, then we can have.
Okay. Yeah. So people can.